if we're going to stop assuming that we know the population variance, then what we're going to have to do is use the data to estimate the population variance. And that seems fairly straightforward, and it is fairly straightforward. The population variance is the average of the squared distances between all the values in the population and the population mean. Okay? So the obvious way to estimate that would be to take the values in my sample and see how far they are from their mean on average squared. Okay, so I can take each value in my sample, subtract the sample mean, square those, add them up, and it seems like the obvious thing to do would be to divide by how many there are. And this is almost the way we estimate sigma squared. It's almost the way we estimate the population variance. But it's not quite. It turns out that the quantity we actually use divides by n minus 1. And we call it s squared. So s squared is an estimate of the quantity we've been calling sigma squared. S squared is an estimate of the population variance that we can calculate using the data that we actually obtain in our sample. So the first thing to say about this n minus 1 on the bottom is that if our sample is pretty big, this really doesn't matter at all. If we take the sum of these squared differences and divide by 999 as opposed to 1,000, we get the same number. So the real thing to understand is that this is not a big deal, practically. Okay, but what can we say about it? Why is that there? Why do we use that n minus 1 instead of n? So I'm going to try to give you intuition in a couple different ways. Here's one. If we repeatedly sample from the population, and instead of writing down y bar, the sample mean, we write down this thing, s squared. If we do that process 1,000 times, sample from the population, write down s squared, we'd have 1,000 values of s squared. And we could take the average of those. Only if we use this n minus 1 will that average be equal to sigma squared. And we can show that mathematically as well. Only if we have an n minus 1 on the bottom is it true that the expected value of s squared is equal to sigma squared. And this property, that the expected value, the mean of our estimator, is equal to the true value, is called unbiasedness. So one of the reasons that we use an n minus 1 in this denominator is that the estimate we obtain is an unbiased estimate of the population quantity. And that's a nice thing, right? That's a helpful thing. If we had just an n here, then if we repeatedly sampled from the population and each time wrote down our estimate of the variance, it would on average be a little bit off. And that would be too bad. So that's a nice way to think about this. Okay, what else? One way that people like to talk about this is as pieces of information. So if I have a sample size of 100, then I have 100 pieces of information that I get to use. The problem is that in order to calculate the sample variance, I had to first estimate the sample mean, because the sample variance is based on how far the values are from the sample mean. So I used up one piece of information. Therefore, I only have 99 pieces of information left. Related to this idea that we only have so much information is the word that people use to describe this quantity, which is degrees of freedom. And in order to try to give some intuition for that, I'm going to jump to a totally different context. I'm going to jump ahead in statistics to the idea of regression. Suppose that I'm trying to estimate a line for some data. So the general idea of regression is just here's a bunch of data points, what line should go through them. That's a very loose way of describing what regression is, but that is what it is. Okay? So clearly, if I only had one data point, that is not going to be enough to tell me anything about the slope of this line or how data varies from the line or really anything. But if I had 2 points, then I could estimate the slope. Right? However, there would not be any information left over to talk about how much the points are likely to vary from that line. If I want to talk about how much points vary from a line, then I need 3 points. And now I can estimate the slope and also talk about the variance. So this idea of degrees of freedom is the idea that there's only so much freedom left for kind of where a line could go or how much evidence you have after you've used up some information, say, to estimate the line. So in this case, In this case, if I've estimated the slope of the line, that used up a couple pieces of information because it takes 2 data points to draw a slope, and I have 1 more piece of information left over to estimate the variance. So here we don't have a regression, but you can think of it as a number line. If I only have 1 data point on this number line, I could estimate the mean. My estimate would be exactly equal to that value. But only if I have 2 data points do we have an estimate of the variability. But it took 2 data points to do that because one of those data points gets used up for estimating the mean itself. So that intuition gets us toward understanding why we have an n-1 here. There's one more way I like to think about this n-1, and this one is my favorite way. What are we going to do with this s squared? We're going to use it to assess the uncertainty, the error, in our estimate of the mean. In that quantity y bar, we're interested in how much variability it has. And we're going to use s squared to help us do that. But what we really want to know is how much these values deviate from the population mean. The problem is we don't know what the population mean is. So if we're thinking about how much the points deviate from the population mean, and now we're thinking about how much these points deviate from our estimate of the population mean, there should be more uncertainty in the calculation that comes from estimating that population mean rather than using the population mean itself. Again, if we think about how much the values deviate from some known number, there's less uncertainty in that than how much the points deviate from my estimate of that number, because maybe my estimate's a little bit off. So what's happening with this n-1 here? Well, we're taking this numerator and we're dividing by a smaller number than we would otherwise, a smaller number than we would had we not subtracted 1. If my sample size is 100, here I'm going to divide by 99. What does that do to this entire quantity? Well, when you divide by something smaller, the overall number is a little bit bigger. In other words, because we have to estimate the mean, because we're estimating the thing that the points are deviating from, we're inflating this entire estimate of the uncertainty just a little bit to reflect the fact that we have more uncertainty than we would if we knew what the points were deviating